Well, hello and welcome to this math course. We are going to begin our discussions by talking about limits. Now, limits are something that are required in order to understand derivatives and integrals better, which is why we are talking about limits first. The idea of a limit is basically asking the question, what happens to the y values of a function as the x value gets close to a certain number that is given to you? So let's look at a simple example. If I'm given the function y equals x squared, what's going to happen to the y values as the x values approach 2? So if I look at this function in a calculator, I can look at the table, I can look at the graph near x equals 2 and kind of figure out what's going on. So here's a table and here's the graph that would be produced by y equals x squared. And I'm looking at the y values as the x values are slightly less than 2, but approaching 2. And there's a bit of a pattern there. And then I'm also looking at the y values for x's that are a little bit bigger than 2, and again, getting closer and closer to 2. And what you'll notice is whether I approach from the left or from the right of x equals 2, the y values approach 4. And as I look at the graph, I notice the same thing. As I look at the y values as x approaches 2 from the left or from the right, the y values approach 4, and the function actually exists there, and the y value is 4. Okay, so here's the first strategy that you would use when you are evaluating limits. If you can replace x with the value that you're given, then go ahead and do that. But if it causes an error when you do that, you have to rely on a different strategy. So that's all you really need to do here. If you have x squared and x is approaching 2, and that's your limit, then you can go ahead and replace x with 2, and you get a y value of 4. All right, another example, if I'm taking the limit as x approaches 5 of 2x plus 1, all I really need to do is replace x with 5, and I get a y value of 11. So that's the first strategy. Now here's a different example where the first strategy won't work. If I have x squared plus 5x all over x, what's going to happen to the y values as x approaches 0? Well, obviously I can't substitute x equals 0 in because I will get 0 over 0, and that is indeterminate. And you can see that by looking at this table. I'm looking at x's that are a little bit less than 0 and x's that are a little bit bigger than 0 to see what's the pattern with the y values. So you'll notice that as x gets closer and closer to 0 from the left or from the right, you'll notice what happens to the y values. The y values get closer and closer to a y value of 5 from either the left or from the right. And you'll notice that in the graph as well. If I approach x equals 0 from the left or from the right, the y values approach 5. Now in this case, the function doesn't actually exist at x equals 0, but the y values do approach 5. So we call that a discontinuity. All right, so here's a second strategy that you can use. If you can't substitute the x value into the function, then maybe what you can do is you can factor the numerator and the denominator completely to see if any of the factors cancel out. So in the case that we were just looking at, we're taking the limit as x approaches 0 of x squared plus 5x all over x. The numerator can be factored to give you x times x plus 5, and what that does is it allows me to cross out the x on top and on the bottom. Now notice you can't cross out factors in a fraction if they're both equal to 0, but luckily x is approaching 0, so it's not actually equal to 0, so I can go ahead and cancel those out. So what I'm left with is the limit as x approaches 0 of x plus 5. Now I'm in a position where I can just replace x with 0, and I get 0 plus 5, and that's 5. So as x approaches 0, y approaches 5, as we saw in the graph and the table. So that's more of an algebraic proof of that. All right, so in another example, if I have x squared plus 5x plus 6 all over x plus 2, what's going to happen to the y values as x approaches negative 2? Well, I can factor the top again into x plus 3 times x plus 2, and now the x plus 2's can cancel out. Remember that x does approach negative 2, but it's not equal to negative 2, so those factors aren't actually worth 0. They're worth something close to 0, and I can cross them out. All right, so what that leaves me is is the limit as x approaches negative 2 of x plus 3. So now I can just replace x with negative 2, and I get negative 2 plus 3, which is 1. All right. Another strategy, if you have multiple fractions within your function, you might want to try and find a common denominator. Here's an example of that. If I have the limit as x approaches 0 of 1 over x minus 3 plus 1/3 all over x, of course I would try and replace x with 0, but what that's going to do is it's going to give me 0 over 0, which is indeterminate. So this is where I would use a common denominator to write the function as something else. So the common denominator on top is going to be 3 times x minus 3, and I change my numerators accordingly, and then I can write that entire numerator as one big fraction. 3 plus x minus 3 all over 3 times x minus 3, and all of that is still over x. But notice that the numerator in that fraction can be simplified to just x. The denominator of 3 times x minus 3 will stay the same, and there's still an x on the very bottom. But what you notice now is that there's an x on top and bottom that can be canceled out. So you're left with 1 over 3 times x minus 3. So now I'm in a position where I can replace x with 0, and I get 1 over 3 times 0 minus 3, which is negative 1/9. So in this function, as x approaches 0, the y values approach negative 1/9. You'll notice that, again, it doesn't actually get there. The function doesn't actually exist at x equals 0, but the y values do approach negative 1/9. All right. If you have multiple square roots in your function, you can try multiplying the top and the bottom by the conjugate of whatever is in your function. So in this case, I've got the limit as x approaches 0 of square root of x plus 5 minus root 5 all over x. Again, I would always try to replace x with whatever number is given, but if I do that in this case, I get 0 over 0. So now I'm going to try multiplying top and bottom by the conjugate of the numerator. So that means I'm multiplying top and bottom by root x plus 5 plus root 5. And what that gives me is x plus 5 minus 5 on the top, and x times root x plus 5 plus root 5 on the bottom. Now the numerator, the 5's can cancel out, the plus 5 and the minus 5, leaving me with just x over that same denominator. And now both the numerator and the denominator have a common factor of x, which can be canceled out. And I have the limit as x approaches 0 of 1 over root x plus 5 plus root 5. And finally, I'm in a position where I can replace x with 0 and evaluate the function. So if I do that, I get 1 over 2 root 5. So in this function, as x approaches 0, the y values approach 1 over 2 root 5. All right. Another strategy, if you see you have parentheses in your function, you might try expanding those. So if I have x minus 7 squared minus 49 all over x, if I were to replace x with 0, I would get 0 over 0, so I'm going to have to find another way to do it. So let's expand the parentheses, and I will get x squared minus 14x plus 49 minus the 49 that was already there all over x. The plus 49 minus 49 simplifies to 0, so I've got x squared minus 14x all over x. That can be factored to x times x minus 14 all over x. And again, the x's can cancel, and I'm left with the limit as x approaches 0 of x minus 14. Now I'm ready to replace x with 0, and I get 0 minus 14, which is negative 14. Okay? So some strategies to help you evaluate limits if they exist. If you have any questions, please let me know, and I will see you tomorrow.